Hello, Tanya Laird here, and welcome to Part 3 of Lecture 16 of ENGR 231 Engineering Statics. In this portion of the lecture, I just want to finish up Lecture 16 by working through some more examples of moments of inertia, and also looking at some integration techniques and tools that can help us solve, in particular for IY, or IX, where we normally have to use horizontal differential elements, and there is a way, basically a little trick we can use to get vertical differential elements, which does make this a lot easier. Okay, so building up what we've seen in Part 1 and Part 2, I think I'm going to go over a little bit of integration tips and tricks first on this. Moment of inertia here. So first of all, we have our two basic formulas. Ix is equal to the integral of y squared dA, and Iy is equal to the integral of x squared dA. Now, by default, this is going to involve a differential element that is like this. If we have an area, just some generic area, or maybe something like this, and I want to find the moment of inertia with respect to the x-axis, normally I'm going to be taking a horizontal differential element here, a horizontal dA. And so normally my dA would be like, it would be in terms of y. We would have a y squared, and then we'd have a dy, and then something, a function for the width of this in terms of y. Which this can be useful, but often, sometimes this isn't too bad. So for example, in the previous portion of the lecture where we looked at taking the moment of inertia of a rectangle, well, that really wasn't too bad. But especially in cases where you have complex functions or complicated functions, nothing imaginary here, where you have very complicated functions or graphs, sometimes it can be very difficult or make the integration very difficult if you have to solve for one of those functions in terms of y instead of in terms of x. So I'm going to show you a trick for turning this into a vertical differential element. And Iy usually isn't quite as bad because in most cases we can use a vertical differential element. So we can just use a vertical differential element, and because our equation is often provided in a y equals x form anyway, a standard function, we can just have a dx, and that works quite well. And this would just be this was your y here, that would just be the difference in height. And again, if this, assuming this is based on the axis, this is off the axis here. If it was, there was a gap, if there was another function down here, then of course y is the difference in height between the two functions. Anyway, I would like to demonstrate variable transformations, or coordinate transformations, or let's see, I'm trying to think what the best word for this would be. Maybe I should say axis transformations, or differential element axis switch. For Ix calculation. So this is going to go back to something we derived last time, which is the moment of inertia of a rectangle with respect to the x-axis. But more importantly, the moment of inertia of a rectangle about its own base. We saw in part 2 of this lecture that if you depending on where you take the moment of inertia about, you will get different results. And we know that we found that the moment of inertia, or I should say for a rectangle, Ix is going to be equal to b h cubed over 3 when you are doing this about the rectangle's base. And we can actually use this then as a way of sort of shortcutting or cheating the basic Ix formula. See, what we could do normally with the Ix, what we do is we say, okay, well, we take we have something kind of like this. We have our function, and we just do horizontal differential elements, adding up the moment of inertia of each of these pieces and integrating across the function. But what we can do instead is we could just directly calculate the Ix of each of the, or we could use vertical rectangles, because we already know the, we effectively already know the moment of inertia of a rectangle measured about its base. So what I'm going to do is I'm going to use little dix's here and sum the dix's up as I go along here. So here's what I can do. I can, instead of using basically just a straight dA, I can calculate the little dix's of each of these rectangles. And I know this rectangle effectively, if I'm going to use a dx, has a base of dx and a height of y, whatever the y height of that function is. And so I can then say that dix is equal to not b, but dx there, and then not h, but y, and then the same over 3. So basically, I can say that ix is equal to, or dix is equal to y to the third over 3, y to the third over 3 dx. Y to the third over 3 dx. Now, as far as why would I want to do this, well, y is very easy to get in terms of x. Usually it's given as a function anyway. For example, if this is a function, oh, y equals negative 2x squared or something, it's very easy to just transform that. Very easy to transform that. Or not even needed, sorry, it's very not neat. Yeah, I guess, yes, transform that. All I'd have to do is put in my function into there. And if this is then in terms of x, I have my dx here, and that integral is very easy to work with. So if I integrate both sides of this, the integral of dix is just ix, the moment of inertia with respect to the x-axis, and that would just be the integral of then y to the third over 3 dx, again putting in our actual function in terms of x as a replacement for y here. So what this is a way of getting the both moments of inertia using a vertical differential element. So this is how we can, unlike previously when we looked at horizontal differential elements, which are, especially in functions already given in terms of x, are intrinsically more complicated to work with. This is a way of transforming the variables and working with everything in terms of vertical strips. And that does make things quite a bit simpler. So let's consider an example here of where we might apply this. Oh, let's see, what might we do? In fact, let's actually do something very similar to what we looked at in that previous slide. Let's say I want to find the moment of inertia of, oh, let's call this y equals negative 2x, maybe negative 4x squared. I have the equation y equals negative 4x squared. This region here, this is given. So all this is given. And then I am asked to find the moment of inertia of this region relative to the x and y axes. So, and let's just say these are in units of inches, for example. So let's go ahead and do that. The first thing I'll need to do is to find my bounds. Well, on the left hand, since I am going to try to do both of these in terms of dx, so that's going to make things a lot easier. Now this point here, if I just set negative 4x squared equal to 0, y equals negative 4x squared equal to 0. Wait. Oh, actually that's not going to work at all, is it? What did I want to do? Oh, let's see. Sorry, not the negative 4x squared. Let's do negative 4x squared. Oh, maybe actually plus, what about plus 4 or something like that? Because if I did that, then I did that, yeah, that would work. Let's do y equals negative 4x squared plus 4. Still something that's going to be relatively easy to work through. So I need to find the x coordinate where that equals 0. And so here then, negative 4x squared plus 4. Okay, yeah. Oh, not plus 4, not minus 4. There we go. So negative 4x squared equals negative 4. X squared equals 1. X equals plus or minus 1. Relatively simple. And we're going to use the positive one. So our bounds are going to be from 0 to 1. So working through this then, first I want to do, let's do the IY. IY is going to be equal to the integral of y squared dA, x squared dA, sorry about that, x squared dA, and I can use for this, I can use a vertical differential element by default, even without any modification. And I would have a y here, and that dA, I would have a dx, and then the actual equation, the negative 4x squared plus 4. So negative 4, the dA would be equal to dx times negative 4x squared plus 4. So that's going to be equal to the integral of x squared times negative 4x squared plus 4 times dx. The integral there. Negative 4x squared plus 4, let's see, does that make sense? Yep, negative 4x squared plus 4 times the dx, and the bounds will be from 0 to 1. And so then this is just a relatively straightforward integration, 0 to 1 of negative 4 x to the 4th, negative 4x to the 4th, if I distribute that, yep, negative 4x to the 4th plus 4x squared dx. 4x squared dx. So then, again, that will be a very simple polynomial integral, but I think I might just throw this one in my calculator because I think you know how to integrate a basic polynomial like this. And if I throw this into my calculator, negative 4x to the 4th plus 4x squared, and then in terms of x and integrate from 0 to 1, oh, this will then come to, let me do this in exact mode, 8/15. So negative 4x to the 4th plus 4x squared. Let's that make sense? Negative 4x to the 4th plus 4x squared. And then integrated from 0 to 1, we get 8/15. And the units for this would be inches to the 4th. Moment of inertia has units of inches to the 4th. Again, that's just a basic polynomial integration. I don't necessarily feel the need to work all the way through that. Then Ix. Now, normally Ix, again, would involve doing a horizontal differential element. So if I do the Ix now, Ix would normally, again, look something like this. I would have my equation, and then I would have a horizontal differential element. And this is what we learned to do in part 2 of the lecture. But what I would like to try it here and now is that modification formula, where we say Ix is equal to the integral of y cubed over 3 dx instead of the dy. So Ix is equal to the integral of y cubed over 3 dx, because again, we're just applying a vertical differential element this time. And just like we got in the previous one, we saw that this formula is relatively easy to derive. And then here, so basically instead of using a horizontal differential element and finding the dA and then multiplying by the x squared, we're basically finding the moment of inertia of each strip as we move from left to right. So this equation then would be the integral of negative 4x squared plus 4 and that quantity to the 3rd power divided by 3. And that integrated from 0 to 1. And also dx. So negative 4x squared plus 4. Again, we need to put the entire quantity inside that 3rd power. It's not just we can't integrate a y with respect to x. Well, I suppose you might be able to do by treating it as a constant integration or something, but not even then, that's not proper calculus. But we can't just integrate a y with respect to x. Instead, we need to replace it with its function. And to do this, well, this wouldn't actually be that complex. Well, it would be time consuming. You would first need to expand this out do the triple expansion here, and then work all the way through the integration. Again, although I think this isn't too bad. This is also just polynomial integration, so I don't know if I feel the need to work all the way through that. Again, as a time shortcut here, to try to keep these already lengthy videos down in its length, I think I'm going to just throw this into my calculator pretty quickly here. Okay, so this is negative 4x squared plus 4 to the third power divided by 3. Negative 4x squared plus 4 to the third power divided by 3. And then I'm going to integrate that. Copy, paste, and integrate from 0 to 1. And if you want to do this in ugly decimal mode, that would be fine, but I just left it in exact mode. And that comes to 1,024 over 105 inches to the fourth power. Again, Ix, just like Iy, all area moments of inertia have units of inches to the fourth power. All right, so what if there are, for example, a variety of, what if there are two different curves? What if I have two different curves? How do I handle something like this then? So I want to show you how you would handle finding a moment of inertia for a system if there were a region, if there are two different curves present. But still, two different curves that are, a system that's still within the same, we don't have to do any transformations to different coordinate axes like we will when we look at parallel axis theorem in lecture 17. What about something like this? Let's make an interesting problem. What if I had, how do I want to do this? Let me think about this. What do I want to do here? I have a couple options. Okay, what if I have something that had two distinct regions in it? And let's say I had a, let's say, you know what, I'll do the axes in purple to separate those from my equations. Let's say I have something like, let's make something fun. Let's say I have a parabola, and let's call this y equals 4x squared. Or maybe y equals 2x squared. And then I have an equation. And I also have an equation. Let's say this is y equals let's say 8x. Y equals 8x. And I want to find the moment of inertia of this region here with respect to the x and y axis. So, and let's just say this is also in inches. Find the moment of inertia of this region with respect to the x and y axis. So let's see here. First I would want to find where these intersect, and that would be just 8x equals, if I can manage to write the number 8 properly, equals 2x squared. And so then I would end up with, if I divide both sides by 2, I get 4x equals x squared, not a lambda but an x. And then finally x just equals, well, that cancels out and that cancels out, so x equals 4. So this would be at 4, 32. But we won't actually need to use the 32 because I'm going to do all of this in terms of x if possible. So first of all, we can get the IY. That one's going to be fairly straightforward, just adding up a series of dAs here. So my differential element on this for the IY is a vertical element, very simple. And it has a dx and then a height of, that would be 2x squared minus 8x. 2x squared minus ax. So therefore, dA is equal to 2x squared minus 8x, the quantity, times dx. And therefore, Iy, since Iy is equal to the integral of y squared dA, that would be equal to the integral of Now, in this case, I would need to replace the, well, sorry, not y squared dA, never mind, x squared dA, gotta get my right variables down, that would help. So that would be the integral of x squared times 2x squared minus 8x dx, and this evaluated from 0 to 4. And this evaluated from 0 to 4, so that would be the integral of, from 0 to 4 again, of 4x to the 4th minus 8x to the third, minus 8x to the third, and this is going to be turning out a little bit similar to the last one, but that's okay. Actually, no, it's still different because we still have to, what I really wanted to show here was the fact that you had two different curves, how you would handle that. 4x to the 4th minus 8x to the third, and then dx. And I think I will just also cheat on this one and throw this into my calculator as well. Also, just for the sake of expediency. So integrate 4x to the 4th minus 8x to the third, comma x, and evaluate from 0 to 4. And again, in exact mode, 4x to the 4th minus 8x to the third, I get 1536 over 5. And this is in units of inches to the 4th. And that is our IY, the moment of inertia of this thing with respect to the y-axis. And then finally IX, if I can quit from jumping ahead, IX. And again, we're going to use the modified formula that we saw previously, the integral of y to the third over 3 dx. Now, in this context, the y, again, is the total height of a dA, and that, because we're using a dx, we can do that, and the height of that is just the same, 2x squared minus 8x. The nice thing about this is you can really use the same y's for both of these. And so that's going to be the integral, again, from 0 to 4. And this would also be a very hairy expansion, but that's why I'll just throw it if I can manage to talk properly, throw it into my calculator, and if you want to, if you're working through this, I would encourage you to check out those numbers. So 2x squared minus 8x evaluated from 0 to 4, but this thing to the third power. So I can throw this into my calculator. Let's see, 2x squared minus 8x to the third divided by 3. Let's see. To the third divided by 3. So 2x squared minus 8x to the third power divided by 3, and then integrate this, comma x from 0 to 4. From 0 to 4. And I get a value that really would be better as a ugly decimal. Although something isn't right. What happened? I got a negative number, which doesn't make sense in terms of a moment of inertia. So we need to figure out what went wrong. What happened there? Interesting. So I'm getting a negative number, which isn't going to be the best idea, or that definitely shouldn't be a negative. So let's see what happened. So when I threw that into my calculator, I immediately got something wrong. I got a moment of inertia in my calculator here of negative 32768. 32768 over 105 inches to the fourth power. So that can't be right. We can't have a negative moment of inertia. That's fundamentally impossible. So first of all, I'll double check to make sure I didn't put it into my calculator wrong, but I don't believe I did. So there's something else going on here, likely with our arrangements of our differential elements and our integrals. So 2x squared minus x to the third power, and evaluated from 0 to 4. Let's see, double check our intersections. Yep, they definitely intersect at 32. So, well, ultimately the main problem with this is that that formula is not necessarily going to work in this particular case. And the reason for that is that, unfortunately, in this case, one issue you're having is that basically we have a, that formula assumed that this formula here, the y to the third over 3, that assumed that we were taking the moment of inertia with something that was bound to the x-axis. So that's not going to work. or was positioned on the bottom of the x-axis. And the bottom region here clearly isn't. The bottom region there clearly isn't. So instead, what we need to do is we can, however, use a subtraction-based approach. So what we can do instead, well, we could go back to using a horizontal element and running through that math, but what we can do instead is we can find the moment of inertia of the line here, of the region that would be defined just by the line, and then the moment of inertia that would be defined just by this area under here, and then subtract the two of them. So basically, I could say this is the integral of, from 0 to 4, of the, of this, oh, actually, that is the problem. What do you know? That is a very big mistake. Sorry about that. This seems to be a very big mistake. And the problem with this mistake is the following. We have a core problem with our dA. It is very important to subtract the top minus the bottom. So I think that other formula will actually work now. 8x minus 2x squared. Uh-oh. Gotta go back to our basic calculus. Top minus bottom. 8x minus 2x squared. There we go. That should work now. 8x minus 2x squared. And so let me go and throw this one in my calculator again to make sure I'm giving you the right answer this time. So x, that would be, let's see, 8x to the third minus 2x to the fourth power. And again, evaluated from 0 to 4. Sorry about that little mathematical typo. Danger of doing problems live. X, 0, 4. Basically, when I'm putting these videos together, I really like to sort of work through problems on the fly if I can. Sometimes it's necessary to come up with them in advance, but I think there's a certain benefit to not having the solutions basically written out in front of me beforehand, and then I can sort of talk you through the thought process that I'm doing as I actually work through these. So sometimes I know that can be, the downside of that is sometimes as I come up with a problem off the top of my head, and the downside of that is, of course, sometimes you end up with mistakes. But anyway, it just goes to show some common errors, and my goal here is to show the thought process of these problems, not just the final answer for them. So this would come to 512 over 5 inches to the fourth power. 512 over 5 inches to the fourth power. So 8x to the third minus 2x to the fourth. And then this evaluated from 0 to 4. Yep, okay. So this one, now for Ix, again, we are still going to use a differential element that is like this. But we're going to be basically saying that dix is equal to y cubed over 3 dx. We're switching the variables, doing a change of variables, because it's intrinsically easier to work with well, not intrinsically, but usually it's easier to work with a dx than a dy. But there are, of course, some exceptions. So let's go ahead and say that the integral of ix is equal to the integral of y cubed over 3, the y cubed over 3 dx, and this would be an integral evaluated from 0 to 4, and the y this time hopefully will be correct, 8x minus 2x squared, this to the third power divided by 3 times dx. And now if I throw this in my calculator, 8x minus 2x squared to the third power divided by 3 and evaluated from 0 to 4. Evaluate with respect to x, and I get a number that should definitely not be, that is, it's not an ugly decimal, it's an ugly fraction. It's a fraction that is impractically large, but I did this in exact mode, so that's okay. So this would be 32,768. Try doing that by hand, getting that exact number, although I guess it wouldn't be too bad, just a bunch of common denominators. And this would be inches to the fourth power, and we now have the moment of inertia with respect to the x-axis and the moment of inertia with respect to the y-axis, and we never needed to use a single horizontal differential element. We didn't have to use a single dy. We were able to do it only with the dx. Finally, I might mention how you had to handle things with multiple regions. For example, what if you had something like this? What if I asked you to find the moment of inertia of a region, a triangular region like this? Let's say with respect to the, well, either the x-axis or the y-axis, either one would be fine. Well, this would be one where the horizontal element would be very inconvenient. But all you would do here, in fact, maybe I can just go ahead and work through this one. Let's say this is at 0, 0. Let's say this is at 2 and then 2. And this is at, oh, not 2, but let's say that is 2 and that is 6. And just for fun, let's say this is all in meters. How would I work through this? How would I find the area, not the area, but the moment of inertia of this triangular region? Of inertia of this triangular region. Well, I can't do this, if I'm going to use a dx, I can't use a single zone of integration. So what I'm going to do instead is to take this, actually though, this is one case where, well, no, even then, that wouldn't, well, I would have to think about that. This might actually be one case where it's beneficial to use a horizontal zone of integration for our IY rather than a vertical one, or sorry, for our IX rather than a vertical one. But anyway, let's look at the IX first. I'm sorry, the IY first. So first of all, I would like to get these equations. This is a 2 by 2 slope coming right in at the origins. So that's obviously just y equals x. Now this equation here, I have 2 points, 2, 2, and 6, 0. So I know the slope here, m, is going to be negative 2 over 4, negative 2 over 4, or negative 1/2, negative 1/2. And then I can say if I want to get the intercept, y equals negative 1/2 x plus b. If I say, okay, put a 0 here and negative 1/2, negative 1/2 times 6 plus b, and b is equal to 3. So the equation of that line is going to be y equals negative 1/2 x, y equals negative 1/2 x plus 3. And if we put in 0 there, we would get 3. If we put in 2 there, we would get 2. And if we put in 6 there, we would get 0. So that is the correct equation. That is the correct equation. So actually, I think I'm just going to go ahead and do both of these. Let me think about that again. Yeah, I guess it wouldn't be terribly difficult to do. I think in this case it would be about the same difficulty doing them, either doing the IX with a horizontal or vertical, but I'll go ahead and show it with the vertical. So here, first of all, let's get the IY, the moment of inertia with respect to the y-axis, and that's just going to be equal to the integral of y squared dA. Now, the tricky part, though, is that we're using a vertical element of integration, and we can't use one equation to describe that dA across the entire thing. Instead, what I'm going to do is the summation, essentially from one summation from 0 to 2 of y squared dA, and plus another zone of integration from 2 to 6 of y squared dA. And then I'll just put in the formulas for each of these. That would be y is just going to, well, dA here for this first one is just going to be equal to, well, let's draw this out a little bit. Here, my dA is like this, and the height of this is just x. And a dA here, but it would still have a width of dx, and a dA here would still have a width of dx, but now its height would be given by the equation negative 1/2 x plus 3. So I would integrate this from 0 to 2 y squared, and of course dAs are just the products of these two. Oh, sorry about that. That should say x. Pearls of recording lectures late at night. Okay, so integral from 0 to 2 of x squared times x dx for our dA there, plus the integral from 2 to 6 of, and that should be another x squared dA, and that would be x squared times the area of, which would be negative 1/2 x plus 3 times dx, times dx, and if I, maybe I'll integrate these separately. So that's basically x to the third. Integrate, let's see, x to the third, comma x, comma 0, comma 2. Well, that's simple enough, that's just 4. And then the integral here, if I expand all that and take the integral of it, f3 integrate, let's see, x squared times negative 1/2 x plus 3, comma x, comma 2, comma 6. And this is then going to come to 48. So we'll have an overall moment of inertia of 52. I said this is in meters, so the units here would be meters to the 4th power. Again, moments of inertia always have units of, or at least area moments of inertia, always have units of length to the 4th power. And then Ix, we could, of course, we could use a horizontal element in this, and in fact that would actually allow us to use a single integral. So, you know what, maybe I could actually give that a go. Let's try doing Ix again but this time, I think it'd be fairly straightforward based on the previous examples to see how we would use a vertical element. We could just put in the same y's as we did before. But what if I want to do this with a single element of integration, or single integral, I should say? A horizontal one for our dx here. Well, basically, if I'm going to do this in terms of y, I need an expression for the width of this in terms of y. Well, first of all, this equation here would be y. Well, I know it is equal to, I know this is y equals x, so that means that is just x equals y. If I solve this equation, let's do that to the side here, y equals negative 1/2 x plus 3. Oh, let's see, that would be y minus 3 equals negative 1/2 x, or x equals, that would be 6 minus 2y. 6 minus 2y. Which means our differential element then, our dA, for the horizontal one, and this again is one of those cases where it actually would be beneficial to solve using a horizontal element. I will have a dy here, and the width of this is just going to be this minus this. So 6, basically right minus left, 6 minus 2y minus y, or just 6 minus 3y. So my dA is equal to 6 minus 3y times dy. And then I would just run through the integral, this time from 0 to 2, but in the y, of y squared dA, but that dA would be this 6 minus 3y, and then times dy. And if I throw that into my calculator, that would be, let's see, y squared times 6 minus 3y, and then 6 minus 3y, then comma y, comma 0, comma 2. And I get a moment of inertia in the y direction, or not in the y direction, sorry, about a moment of inertia about the x-axis here of exactly 4 meters to the 4th power. And that would be my final result there. All right, so I think that'll do it for this portion of the lecture, and I guess for all of lecture 16 entirely. Again, all I wanted to do here was work through a few basic examples, or reasonably basic examples. Reasonably basic, I should say, because apparently I made a few mistakes along the way, as you saw. A few stupid mistakes too, forgetting to put the right minus left or top minus bottom a couple times. Apparently I need to go and retake calculus. So if you have any questions, please let me know. There will be one other lecture following this, which is lecture 17, which will cover our parallel axis theorem of moments of inertia, and that will actually be the last lecture for this current semester. All right, so let me know if you have any questions. Again, hopefully you found this illuminating, hopefully you found this enjoyable, or at least not too boring. And if nothing else, I will see you all next time for lecture 17 of ENGR 231 Engineering Statics. Tom Laird here, signing off. Please let me know if you have any questions, and as always, thank you.